Happy Monday, everybody. Thanks for joining us, listening to Lucas Laurindo. Thank you very much for accepting our invitation. Just a quick introduction of Lucas. Lucas got right now is assistant scientist at University of Miami. Before that, Lucas got his master in physical oceanography from University of São Paulo in Brazil, and then after that he got his PhD from University of Miami in meteorology and physical oceanography. He has been doing a postdoc before at NCAR and using satellite products, output of SIMS climate models, and his expertise really in small scale or multi-scale air-sea interaction. Today, he will present to us one of his recent publication. That's my understanding, Lucas. Yeah, Lucas, welcome and take away, please.
Okay. Thank you very much, Jimbo. Thank you very much for inviting me to be here. It's quite an honor. And the title of my talk is Role of Ocean Atmosphere Variability, Scale Dependent Interactions. Let me share. Okay. Okay. Is that the right screen?
Yes, it looks good.
Okay, thank you. Let's first acknowledge my co-authors, Justin Kamal and Dwayne Thompson, and others. I developed this work while I was a postdoc at NCAR. And okay, let's just start. Climate dynamics, we usually consider that the SST variability in the extratropic is driven by weather via surface turbulent heat fluxes. However, in the past couple of decades, it has become clear that mesoscale ocean currents can also produce SST anomalies that are large and persistent enough to modulate the surface fluxes. And there's more and more evidence that this influence of the ocean on the surface processes can play an active role in both weather and climate. So the main goal of this study was to determine what is the relative contributions of the ocean and atmosphere dynamics for driving SST fluctuations and fluctuations in surface heat fluxes as a function of time and spatial scales. So I'll start with maps. These are from Kurtman et al. 2012, showing correlations between SST and the surface heat fluxes in panel A, and in panel B, correlations between SST rate of change, the SST tendency, and the THF. These are from a low-res simulation, use the TCSM model, where the ocean and the atmosphere are both configured to a 1 degree horizontal resolution. And these relationships can be used to infer if the local variability is driven mostly by oceanic or atmospheric dynamics. In A, positive values indicate that the ocean currents generate SST variability that in turn drives a response in the heat fluxes, while in B, negative values indicate that the atmosphere drives the SST fluctuations via the heat flux. And in the case of the low-res model, we can see that negative correlations dominate almost everywhere except in the sorry about this. I think it's gonna flip back and forth rapidly. The controls here are a bit too sensitive. I apologize in advance. But anyway, in the case of this model, the negative correlations indicate that the atmosphere dominates the variability in the extratropics almost everywhere. But these pictures change if you use a simulation configured with a high-resolution area resolving ocean. Now, panel A shows strong positive values at regions with strong Untitled systems, while B show very weak or near zero values in the same regions. And this suggests that at strong current systems, ocean dynamics dominate variability, although the atmosphere in this case is still dominant at the interior of the ocean basins. Recent studies also demonstrated that these relationships also depend on the spatial skill that you're looking at. And in this slide, I tried to demonstrate this dependence using a high-res CSM data from a high-res CSM simulation filtered in space. So PNOA shows the point correlations between SST and THF. While in PNOB, I removed variability with scales larger than 10 degrees. And when you filter the data, you can see that the correlations drop to almost zero in both locations. And we end up with a map that's very similar to that is produced by a low-res simulation. In contrast, if we do the opposite, if we remove variability at large scales and retain only the ocean mesoscales, we now obtain positive correlations almost everywhere in the ocean. These are, in this slide now, this is our similar results, but for correlations between the SST tendency and the turbulent fluxes. And note that when we do so, when we filter to retain only the large scales, the correlations become more negative, almost everywhere. While if you do the opposite and retain just the mesoscales, we end up with near zero correlations almost everywhere. And anyway, these results indicate that the atmosphere controls the SST and heat flux variability at large scales, while ocean processes dominate at smaller scales. However, before this study, those previous results did not constrain well the scales where the atmosphere-driven variability gives way, transitions to ocean-driven, nor what are the time scales where each regime operates. So the main objectives of the study are to determine the influence of ocean in the atmosphere in deriving the variability, and to investigate, gain some insight on the physical mechanisms that give rise to this scale dependency. And for that, we use the spectral methods to characterize the SST and heat flux variability, and also their covariability across a wide range of spatial and temporal scales. And we also use an idealized stochastic model to interpret the contribution of the oceanic and atmospheric processes to the observed spectrum. So I essentially use two CSM simulations. One simulation is low-res with a 1 degree resolution in the ocean and the atmosphere. The other one is high-res with 1/10 of a degree in the ocean and a 1/4 degree in the atmosphere. Both these simulations, they are pretty long. LR has 480 years of monthly outputs, while HR has 163 years. And I also contrast those results with those computed using a satellite product, the J Ofuro 3, which is 26 years long. This study computed the power spectra of SST, heat flux, and their cross spectra as a function of zonal wave number and frequency. I calculate the spectra at each latitude of a basic mask for the Pacific Ocean that I'm showing here in this map. So I compute the results at each latitude inside this region that's bounded here. And to help interpret the spectra, I use a stochastic model describing the SST evolution. This model is forced by the noise terms NA and NO, which represent the action on internal dynamics in the atmosphere of the ocean. And it is composed of a turbulent heat flux term that encloses the stochastic atmospheric noise, and a radiative damping term that attenuates the SST anomalies over time. Essentially, I solved this model for the Fourier transforms of SST and heat flux, and I obtain analytical solutions for the power spectrum and cross spectrum, which are shown here. I'm showing these equations just to show that all solutions, they depend on the noise terms in A and NO. And previous studies based on stochastic climate models, they force the solutions using white noise. But in this case, I wanted to use noise with a realistic variance distribution in spectral space. And the reason for that is that I wanted to check if the presence of structure in the noise could explain the scale dependency of various interactions that I showed before. And to do that, to generate noise with structure, I decided to define the noise using data from the CSM simulations themselves. So I used 2-meter high humidity for NA because we found that that was not strongly correlated with mesoscale SST anomalies. And we used ocean reflux conversions for NO because we know that it is the primary driver of mesoscale SST variability. Essentially, I compute the Fourier transforms of the signals and plug them into the stochastic models analytical solution. And I then adjust the noise variance to the correct magnitudes by fitting the solutions to the SST reflex spectra from the CSM runs. Anyway, the figure in the slide shows the power spectra of NA and NO as a function of zonal wave number, spatial scale, and in frequency, time scale. Note that they show structure; they're not purely right. The atmospheric noise, it is approximately white in frequency space, but it is strongly red in zonal wave number with much more power over large wavelengths. And you can see that the ocean noise, it is a bit different. It is also red in wave number space with more variance at large scales, but it shows more variability close to these lines here, which are the spatial relations of Raspberry waves. It has this spur variability just following the spatial relations. And okay, let's move to the results. Before showing the spectral results, just start with global maps showing the ratio between the SST variance in HR and LR, panel A is for SST, panel B is for THF, computed the variance without the seasonal cycle. So there are anomalies about the long-term mean and the seasonal fluctuations. And what it shows here is that HR resolves much larger variances than LR in the isotropics for both quantities, notably coincide with energetic current systems. And note that the color scale here is logarithmic, meaning that a value of 1 means that HR has 10 times more variance than LR. And the maps are also very similar with each other, which is consistent with the interpretation that in HR, SST variability driven by ocean processes is driving response to the turbulent heat fluxes. Now, here I'm showing the spectra as a function of zonal wave number. Just for SST, the results for turbulent heat flux is very similar to these. And panel A show estimates for the South in the Pacific, where the black lines from the satellite observations, blue is for HR, and red is the LR. The scale here goes from about 7,000 kilometers to 40 kilometers. Note that all data sets, they resolve similar variability at spatial scales larger than 2,500 kilometers. But as you go towards smaller scales, note that the variance remains high in observations in HR, while it just keeps diminishing in LR. So panel A is just for the South. Panel B show the ratio between the variances in HR and LR, but as a function of latitude. This black line here marks where I got these results from. Note that this difference in variance between HR and LR occurs not just at 40 south, but at most latitudes in the exotropics. And for reference, these dashed lines here, they represent the Rossby radius of the formation in the atmosphere and in the ocean. And it shows that the most significant difference between HR and LR it occurs at scales smaller than the atmospheric Rossby radius. So this slide shows the corresponding estimates obtained using the stochastic model, presenting estimates for HR and LR. Here, the gray lines, they are the power spectral computing using CSM data, while the blue lines are stochastic model estimates computed using just ocean noise, and the red lines are estimates obtained using atmospheric noise. The black lines that we can barely see here are the sum between the blue and the black lines. In panel A, we can see that the atmosphere-driven component is significant at large scales. A characteristic that allows the ocean-driven, but sorry about that. The atmospheric noise is very strong at large scales, but it just diminishes steeply as you go towards smaller scales. And this steep decrease is what allows the ocean-driven temperature modulation to prevail. And this happens at fairly long wavelengths, close to 2,500 kilometers in this case. Panel B is for the low RAS. We see that something similar happens, but the ocean-driven component, the blue line, is much weaker than HR, while the atmosphere-driven component, actually, it's pretty similar in magnitude to that resolved by HR. So now in this slide, I'm showing the cross-spectral statistics between the SST and heat fluxes as a function of latitude. I'm first showing estimates from satellite observations. Panel A shows the coherence, which is a quantity that estimates how SST and the heat fluxes are related with each other. It varies from 0 to 1. If it is 0, it means that they are completely unrelated. If it's equal to 1, it means that they are very together. They are highly related. And the bottom panel shows the phase factor, which measures the phase relationships between both signals. And you can see that at large scales, we see weak coherences associated with a 90-degree phase. However, as you go towards smaller scales, the coherence increases, and you have this band of high coherences here, while the phase goes to near 0. And these are corresponding estimates for the high-res and low-res simulations. HR is very similar to OBS. LR does show similar characteristics at large spatial scales, but it notably misses that band of high coherences that's present in the other data sets. Note that LR shows slightly larger coherences near 40 north and in the tropics, coinciding with smaller phase angles. So to me, it says that LR even tries to do something similar to HR and OBS, but the signal is much weaker. And here in this slide, I'm showing stochastic model estimates, including the combined effects of both ocean and atmosphere noise. I'm asking latitudes close to the equator because the stochastic model is not valid there. But we can see that it resolves similar characteristics than the satellites and high-res results. If you go to the other columns, I separate the influence of ocean noise and atmosphere noise. And we confirm that this band of high coherences reflects the action of ocean processes, while the characteristics at large scales, it arises from the action of the atmosphere. Now, I'm showing estimates obtained as a function of frequency, also just for 40 South in the Pacific, and in this case, just for the HR run. Panel A is for SST, panel B is for turbulent heat fluxes. The gray lines are obtained with CSM data, while the blue and red lines are stochastic model estimates for the ocean and the atmosphere noise. Starting with SST in panel A, we see that ocean noise produces more substantial variability at a period shorter than about 500 days. But as you go towards longer periods, the variability induced by the ocean in the atmosphere, they become more or less comparable, although the atmosphere-driven component is stronger here. In any case, you can see that both the ocean and the atmosphere produce more larger SST variability at lower frequencies, a red spectrum. It is well known that the atmosphere drives this kind of response to stochastic forcing, but here we find evidence that the ocean noise can do something similar. And looking at the heat fluxes, we find that the atmosphere controls most of the variability at higher frequencies, while the ocean controls variability at low frequencies. And to double check our conclusions of the influence of ocean processes, we can filter out large scales and recompute the frequency spectra. And when we do so, note that we obtain spectra both for SST and turbulent fluxes with very similar shapes. And the blue lines here indicate that most of the variability at these scales is driven by the ocean noise. Now this is the coherence between SST and THF that is predicted by stochastic model. This is also for spatial scales smaller than 1,000 kilometers. And these results indicate that SST and THF, they remain coherent and in phase over the entire frequency range that we are analyzing, which goes to about 80 years. And this stochastic model confirms that the highly coherent signal arises from the action of ocean processes. Now, this is our estimates, not from stochastic model, but for observations, HR and LR. This is just the coherence. And again, we see that this highly coherent signal, they are present in observations. HR results a very similar feature, although it seems a bit stronger than shown by observations. While LR just showed these very noisy signals, which indicates this is dominated by noise, essentially. And the bottom is just the corresponding estimates obtained using the stochastic model, which also shows that these high coherences are coming from the influence of ocean processes. So the conclusions, sorry about that. We found in this study that the atmosphere dominates the SST and THF variability at spatial scales smaller than about 2,000 kilometers. That in HR and observations, ocean processes control most of the variability towards small scales. The ocean can prevail at these scales because ocean forcing is strong, while the atmosphere forcing is much weaker than what we observe at large scales. We found that the atmospheric erosion grades of the formation seems to be a relevant scale, controlling the transition between atmosphere-driven and ocean-driven variability, although we still don't have a good explanation of why that is the case. We found that ocean processes can drive oscillations in SST and on the heat fluxes over time scales ranging from interseasonal to multi-decadal over much of the subtropics. And finally, we find that the influence of ocean processes in the lower Earth simulation is much weaker than that implied by satellite and high-res results. Is it? Thank you for going over, sorry for going over time, and thank you very much. Showing here my email if you would like to contact me, and also the reference for the study. Thank you very much.
Thank you very much.
Yeah. Thanks, Lucas. Yeah, so I just wanted to thank Lucas and open the floor for comments. If you can raise your hand in the chat feature. Irana, I'm sorry.
Just a silly technical question, because I've since I haven't done that before. When you do your correlations, how do you select for spatial scales, larger versus smaller? I guess the same way that you do it for, I mean, I know how to do it for time. Sorry, it's just silly technical.
Oh, no, not at all. I use a spatial filter in the same way that you can filter the signal in space. You can use like a box moving average filter to attenuate a high frequency variability. You can do the same in spatial scale.
Spatial fields. So it's as if you're averaging over everything smaller than 10, then, you know, if you have a 1,000 kilometers per 1,000 kilometers, is this like vaguely speaking, like you're averaging inside this box?
Yeah. We can do this like this is the easiest way to select the scales. But when we were developing this research, we found that it's not very easy to interpret what scales are being filtered, you know. So we try to use a better filter, like a Gaussian filter in space, just so we can really select what scales we are retaining. Sorry. I hope I
No. Yeah. It's good. And then you can do it selectively. I see. And then your picture was showing, that can you explain once more the one where you have both the atmospheric Rossby radius of deformation and the ocean one?
Sure.
What was the meaning there in the end? Yeah, the one on the right. Yeah.
This is the power spectra of SST as a function of zonal wavelength. And I'm computing that for every latitude within in the Pacific. And then I just made a plot like this one, showing the ratio. And what I'm showing here, the Rossby radius of the so I'm not filtering the data here. I'm just computing the spectra as a function.
I see.
Yeah. To generate this kind of visualization, I don't need to filter. Just compute the spectra, and yeah, here is showing me like the difference between variants, like the scales where each model where the variances differ between each of the models.
But you're saying above the atmospheric Rossby radius of deformation, what happens?
I mean, above, you mean larger scales? From the analysis, like I use the stochastic model just to interpret the spectrum. And when I do so, I can break it down. Okay, this is driven by ocean noise or atmospheric noise. And what we found that most of the variability at large scales, the SST variance here, is driven by the atmosphere, by atmospheric processes. But as you go towards scales that is smaller than the forms of variability smaller than atmospheric Rossby radius of deformation, in the high-res model and in the observations, the variance here is driven by ocean processes. And the reason that the low-resolution model does not resolve this, like has so little variance over the scales, is because mesoscale variability is very weak, so it does not really move heat around as much.
Got it.
Okay, we do have a couple of other questions as well. Jimbo?
Oh yeah, just quickly. Yeah, thank you very much, Lucas. This is great work. I just have a question in general. You have shown the influence of the high resolution simulation both in atmosphere and ocean in the air-sea coupling process. But as we know, climate model is mostly low resolution. How to really solve this problem, either through parameterization or other method? What is your take, and what is the community's proposed approach for addressing this question?
One solution is just go high res, just to alleviate these biases. But there are the community, even been talking to colleagues to how parameterize this effect in a intermediate resolution like 40 degree or even low resolution. But it's not clear how to do this yet, as far as I know, using parameterizations. But I don't know. I think that's possible.
Thanks, Mike.
Sergey, did you want to ask your question or make your comment?
I have a quick question. When you were comparing the HR to low resolution variance, you focused on the places where HR had more variance. But in several cases in the ocean, the opposite was true. Can you comment why would low resolution run had more variance in these places?
You're saying that why the low res might have more variance than the high res?
Like everywhere in the tropics, it seems like it has more variance.
Yeah. We discussed this in the paper that where we presented this variance map, these simulations actually. I think we discussed about not associated with the climate mode variability. We speculated that might be something in the way of how we process mixed layer mixing or something like that. But yeah, we don't know. We haven't really explored that.
Okay, thank you.
Are there any other questions or comments? Well, Lucas, I want to thank you again for joining us, and I'll just do my hand clap here. And we will be posting this webinar on our YouTube channel so others can view it. So anyone who's on here that would like to have someone listen to this, it'll be posted here next week when Sam returns from his vacation. So I want to thank everyone for joining us today, and ask that all the pause panel members stay on the WebEx call because we're going to have a short meeting following the webinar. So thanks, everyone. Enjoy the rest of your day.
Thank you so much. Bye-bye.